Lifetime L hours of a battery has a normal distribution with mean 18 and standard deviation 4. So we can write it like this. Alice's calculator requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. Find the probability that a randomly selected battery will last for longer than 16 hours. Okay, this question gets pretty complicated, by the way. I think it's the toughest normal distribution question that I've seen on Edexcel because of what is about to come up. But they're starting out actually quite gently. We're just finding the probability that L is greater than 16. And so remember, we've got our normal distribution. It's centered at 18. And we want to find this area here under the curve, but our calculator does all of that for us. So menu, distribution, it's a normal CD. Lower is going to be 16. Upper is just going to be a big number. Standard deviation 4 and mean 18. The calculator performs an integration under a curve and gives us 0.691. Gee, I'm going to write a few more figures down, 69146, then round it. This is where the question starts ramping up in difficulty. We're told at the start of her exams, Alice puts 4 new batteries in her calculator and she's used her calculator for 16 hours but has another 4 hours of exams to sit. Find the probability that her calculator will not stop working for Alice's remaining exams. So we want to find the probability that it's going to last for 16 hours and another 4 hours. So that's 20 hours. So L has to be greater than 20, or greater or equal to 20, remember it's the same thing, given that we know it's lasted for 16. So given L greater than 16. Now this is the probability for one battery, so we are going to have to bring in the fact that it's going to have to apply for all 4 in a minute, but let's just deal with one for the moment. Now remember the conditional probability formula, actually it's given in the formula book. Probability of A given B is the probability of A and B divided by the probability of B. Because we've reduced the sample space, B has happened, so we can ignore where B has not happened. We scale the probability accordingly by dividing by the probability of B. So for us, it's going to be the probability that L is greater than 20 and greater than 16. Well, that's just greater than 20, because if it's greater than 20, it is greater than 16, divided by the probability that L is greater than 16. And we've got this one already at the bottom. It's 0.69146. That's why I didn't, you will get away with using the rounded version, but really you should use the non-rounded version to avoid errors in your third significant figure. I say you'll get away with it, you might not, okay? So yeah, this is just good practice, just please do it. And for the probability that L is greater than 20, just go back to here, change this 16 to 20, and we get 0.30853. Okay, and then do a little division, and this gives 0.44620. Now I'm not rounding that because that is not my final answer. Remember, this is just for one battery. We need it to happen for all 4. And so you can imagine like a tree diagram, first battery, second battery, third battery, fourth battery, and we need all of them to not fail. So the actual answer is going to be 0.44620 to the power of 4. This gives 0.03963. That's gonna round it because I'm running out of space. Yeah, actually, it's only a 4% chance that the battery's going to make it through all of the exams, given that it's made it through the first 16 hours. Right, now one final even tougher bit. Alice only has 2 new batteries, so after the first 16 hours of exams, although her calculator is still working, she randomly selects 2 of the batteries from her calculator and replaces these with 2 new batteries. Show that, at least we're given the answer here, show that the probability that a calculator will not stop working for the remainder of her exams is 0.199 to three significant figures. So she's randomly replacing two of the batteries. We don't need to think about the arrangements here. It's just that two are still there and two have been replaced. And now we need to find out the probability that the two new batteries are going to last the extra 4 hours. So the probability that L is greater than 4. That's what we need here. This is going to be very high because it's very likely to have lasted this long. Oh, sorry, back to distribution. Lower is now 4. We get 0.999767. So we've got two old batteries, two new batteries, and we need the whole calculator to continue to work. And therefore, it's going to be very similar to what we did above. We need the first, remember, the order's not going to matter here. Just say, let's just look at the first new battery. The probability that it's going to last to the end of the exams is going to be 0.999767. For the second new battery, it's going to be the same. So we're going to be squaring. And then we're going to be timesing by that 0. Where's it gone? 0.44620, the old batteries. And then because there's two of them, we're going to be squaring that as well. And this is going to end up being our answer. So it gives 0.199, and then load of zeros. So just round it. So 0.199. Cool, well done. Right, final bit of the question. After her exams, Alice believed that the lifetime of the batteries was actually more than 18 hours. She took a random sample of 20 of these batteries and found that their mean lifetime was 19.2 hours. Stating our hypotheses clearly and using a 5% level of significance test Alice's belief. Well, actually, we're back into kind of more traditional territory now. You would have done many a hypothesis test, and let's go for it. H0 is going to be that the mean is still 18. H1 is then going to be that it's more than 18 because her suspicion is just that. We've got a 5% significance level and it's one-tailed because it's just a greater than. So under H0, or you could say assume H0 is true, that we've already, remember, got L from before. I'm just going to write it out again. We had 18 and 4 squared. But remember, we're not dealing with L here exactly because we are taking 20 trials of L and then finding the mean. That means we have to look at the sample distribution, which has the same mean, but it has a variance of 4 squared over 20, meaning the standard deviation is 4 over root 20. I always like to just give a very quick explanation of where this has come from, because often people just, actually, I got to say, pretty sure when I did A level, I remember doing this and I just learned to do it. And I'm sure maybe I got told at one point, but I would have forgotten. But it's always interesting to come back to it. So this is L, and its focus, its mean is 18, so it's centered at 18. And then I am taking like lots of values along this curve. And mostly they're going to be around the 18. There's going to be some at the upper end, there's going to be some at the higher end, and then what we're doing is finding the mean of that. So the mean is going to end up like clustering around the middle. You're unlikely to get 20 values and get a value around here. And this is why you get a new distribution. It's going to sort of just have the same area underneath, but I mean, it's going to be even more exaggerated than that. But the peak is going to be at 18, but there's going to be a very high probability because the ones that are at the higher end are going to kind of cancel the ones at the lower end. You're going to get more around the middle anyway, and that's why you get a smaller standard deviation for this distribution. So that you must use that. And then let's find the probability that L bar, this is the mean of our lifetime of the 20 batteries, is greater than 19.2. What are the chances that that could have happened just due to natural variation? And we've got one final normal distribution calculation. So now the lower end is going to be 19.2. Keep that upper as it is. Change this to 4 divided by root 20. The mean is going to stay exactly as it is. And we get 0.08985. Actually, there's a 9% chance that we could have had this mean that's greater than 19.2. This is much more than 5%. We've taken quite a small sample here, I guess. Yeah, that is quite a high probability. But what that means is, so there's enough chance that it happened due to natural variation to say, you know what, that it probably is the case that the mean is 18, or like there's not enough evidence to show it's not 18. Whereas if we got a very small probability, like 0.001, we're saying, you know what, there's not much chance of that happening. And so actually it's the fact that it did happen probably means that our original assumption was incorrect. You'd be in the critical region. In our case, we're above 5%. I'm just trying to explain because sometimes people don't know when, like, they just learn when it's higher to reject, sorry, to not reject H naught or whatever. I'm trying to explain why. So in our case, we're going to do not reject H naught. You get away with saying accept H naught, but strictly speaking, we just haven't shown enough, just not got enough evidence. We'd have to maybe do some more trials, but we never actually accept the hypothesis. So do not reject H naught. Insufficient evidence. At the 5% level, that the mean lifetime is greater than 18. Okay, I've got to say, great question. If you did struggle with it, leave it, come back to it. That's the same with any questions that, are really challenging. Maybe do some more practice on the probabilities. It's bringing in different aspects here, doing a conditional probability, and then realizing that you have to raise it to the power of 4, and then later on, bringing in like a different probability and then timesing those two. Good news is we didn't have to think about arrangements or anything. We just times these 4 probabilities in the end, and it worked out. But there we go.